All right, example 3 is straight from your book. So if you want to look at your book, you can see how they do the example. I'm going to do this a little bit differently. So um, it's just, I feel like it's easier, but you can decide. So in this case, we have a 28-meter uniform chain with a mass density of 2 kilograms per meter dangling from the roof of a building. And it's asking how much work is needed to pull the chain up to the top of the building. All right, so I don't know. Sometimes it's nice to have a picture. So there's my building. Here's the ground. All right, and then we have this chain. So I'll just draw kind of a chain hanging down here. This is my chain. All right, and the chain is 28 meters. 28 meters. Okay, so that's the chain, and we're going to drag this onto the roof. Now, we're going to take this and kind of pull it onto the roof. And so, once we've laid the chain on the roof, now it's not part of the weight hanging down anymore. So essentially the force required is going to change because the weight of the chain is being reduced because you're taking part of the chain and putting it on the roof. So you're gradually just pulling this chain up. And then the amount of chain left determines the amount of weight, which is going to determine the amount of force it takes to pull the rest of the chain. So now in your book, they do it a little bit differently. They take this chain and they slice it into little pieces and they look at how much work is required for each piece, which is a good way to do it. But here's another way to think about it. So I'm going to look first of all at the initial weight of the chain. Of the chain. Right? Because that's essentially what the amount of force it's going to take to hold the chain just in position, at the starting position, right? So essentially we have a 28-meter chain, and we're going to multiply that times its mass density, which is 2 kilograms per meter. Now, because this is mass density, right, if we take 28 meters times 2 kilograms per meter, that gives us the mass, but we want the weight, right? Because we want to find out how much force it takes to pull it. So we're going to take that times 9.8 meters per second squared, which is the acceleration of gravity. And when I calculate that, I get 548.8 newtons. Okay, so that's the initial force it takes. So what I'm going to do is I'm going to graph this and show you the variable force, right? We have a variable force. So if I graph force versus the distance that we've lifted this chain, essentially you're going to start out here at 548.8 newtons, right? And then when you're all done, you basically have pulled the whole chain onto the roof. So after you've pulled 28 meters of chain onto the roof, you'll have zero force left. It takes zero force to, because you pulled it all onto the roof now. So essentially you can think of this as being a variable force, and this is just a line, right? Because the mass density is constant and we're pulling it at a constant rate and all of that. So the force is just equal to the equation for this line. So the y-intercept is 548.8 newtons, and then the slope, is just, now it's downhill, so we get a negative rise of 548.8 and a run of 28. So essentially our slope is 548.8 over 28x. Now I'm going to simplify this a little bit. I'm going to rewrite this as 548.8 minus, if I divide that slope, I get 19.6x. Okay, so that's the equation for our force, right? That's how the force is changing as we pull the chain onto the roof. So I'm just going to integrate that variable force. I'm going to integrate it from 0 to 28, and I'm going to integrate 548.8 minus 19.6x dx, okay, to get my work, right? So when I integrate that, I get 548.8x minus, now I'm going to get 19.6 divided by 2, which is 9.8 x squared. And I want to evaluate that from 0 to 28. And when I put that into my calculator, I get 7,683.2 joules. Okay, so they get the same answer in your book, they just do it a little bit of different way. So I guess it makes sense to me to think of this as a variable force and find the work by integrating this variable force. Because the force varies as you pull more and more chain onto the roof. You get the rest of the remaining chain weighs less and less. So you can take a look at how they do it in the book and decide, what makes sense to you. It's good to be flexible in your thinking. So I wanted to show you a different way to do that problem.